Hello, everyone, and welcome to today's SANS webcast, NIST Recommendations for ICS and IIoT Security, sponsored by CyberX. My name is Carol Auth of the SANS Institute. Today's featured speakers are Phil Neve, VP of Industrial Cybersecurity for CyberX, and he will be moderating today's webcast. And Michael Powell, Cybersecurity Engineer at the National Cybersecurity Center of Excellence at the National Institute of Standards and Technology. If during the webcast you have any questions for our presenters, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Michael.
Okay. Good afternoon. My name is Michael Powell. I'm the Manufacturing Sector Lead here at NIST, NCCOE. Today I'm going to discuss NIST recommendations for securing manufacturing control systems using behavioral anomaly detection. A quick overview of our agenda. I will discuss the NCCC overview, cyber risk to manufacturing organizations, why stronger ICS cybersecurity is needed, benefits of behavioral anomaly detection, NIST test beds that were used for the build, the process control system, and the robotics, and I will touch on cybersecurity framework mapping for this build. The NCCOE assembles experts from businesses, industries such as CyberX, which did a great job at helping us with this build, academia, and other government agencies to work on critical national problems in cybersecurity. This collaboration is essential to exploring the widest range of concepts. Our engagement and business model. First, define the problem. We define a scope of work with industry to solve a pressing cybersecurity need. Next, assemble. We assemble the team of industry, government agencies, and academia institutions to address all aspects of the cybersecurity challenge. Next, we build. We come together in a lab to build a solution and document our findings in our NIST documents, which could be a practice guide or a NIST IR. The build is practical, usable, repeatable implementation to address the cybersecurity challenge. Next, we advocate our implementation. Advocate the adoption of the example by going to lectures and speaking with fellow colleagues to have them implement the guide. We currently have 2 manufacturing projects right now, and I will briefly discuss them later. I want to point out the email to engage with us on our projects and to collaborate with us. Excuse me. I will briefly discuss at a high level this NIST IR, Behavioral Anomaly Detection. Securing manufacturing industrial control systems. Right now, as I said, we are in the advocate stage. And the goal is to provide a cybersecurity example solutions that businesses can implement or use to strengthen their cybersecurity in their manufacturing processes using behavioral anomaly detection tools. This document is in its final stages and should be released March of this year. You can download a draft right now on the website as shown on the slide. For this use case, we use 2 distinct but related manufacturing demo environments, the collaborative robotics system and a simulated processing system, which Phil from CyberX will discuss a little bit more once he talks about the use cases. The behavioral anomaly capability is achieved by 3 different detection methods. Network-based, which was used by CyberX, agent-based, and historian-based. Our goal was to make sure we are addressing cybersecurity risk to manufacturing organizations. Behavioral anomaly detection mechanisms support a multifaceted approach to detecting cybersecurity attacks against ICS devices on which manufacturing process depend on in order to permit the mitigation of those attacks. Introducing anomalous data into manufacturing process can disrupt operations, whether deliberately or inadvertently. More sophisticated hacking tools and techniques are readily available for download from the internet, and the growing cyber dependency makes it critical for attacks harder to stop. The NISTIR is intended to help organizations accomplish their goals by using anomaly detection tools. As you can see, there are many different such, but I will only discuss 2. Detect cyber incidents in time to permit effective response and recovery, and to reduce opportunities for disruptive cyber incidents by providing real-time monitoring and anomaly detection alerts using these tools. The environments that were used, the process and control system, emulates an industrial continuous monitoring manufacturing system, a manufacturing process to produce or process materials continuously, where the materials are continuously moving, going through chemical reactions, or undergoing mechanical or thermal treatment. Next, the collaborative robotics system, which consists of 4 distinct machining stations, 2 machine tending robots, and a supervisory PLC Modbus TCP. It also has HMI and several servers for executing. I like the little video here that shows them actually working in action. We mapped the behavioral anomaly detection capabilities to NIST cybersecurity framework. This mapping allows manufacturers to align cybersecurity activities with businesses' requirements, risk tolerances, and resources. The profile provides a manufacturing sector specific approach to cybersecurity from standards, guidelines, and industry best practices. Finally, I wanted to talk about our new project description that we have coming up, which hopefully should be out. It should be out next month for public comments. The name of the project is Protecting Information System Integrity in Manufacturing Environments. This project explores methods one could deploy to help prevent, mitigate the threat identified as it pertains to deploying cybersecurity capabilities in an ICS manufacturing environment, which CyberX hopefully will be taking part in this build with us also. That is all I have. Phil, if you would like to take over.
Thank you very much, Michael, and kudos to the NIST NCCOE team for putting together this project. I think raising visibility for the need for stronger security controls is an important mission, and you guys are doing an awesome job, so thank you. My name is Phil Nere. I am the Vice President of Industrial Cybersecurity at CyberX. And what I'm going to do today is talk a bit about our company, our technology, and how specifically our platform was used to identify anomalies in the NIST testbed environment. I'm going to give you some examples of that. But first, I'm going to start with a little context just about who we are. We were founded in 2013. We're based in Boston, and we're the only firm in our space, ICS security space, that has a patent for its threat-aware analytics. Our customers tell us that we have a simple and mature solution that interoperates with what they already have in their environments, both on the OT side with respect to the diversity of automation vendors and in their security operations center. And so the part about the patent is important because that's really what we're talking today. We're talking about behavioral anomaly detection, which requires new and more sophisticated form of analytics than we've used in the past with, for example, signature-based solutions or solutions that require configuration of rules. We're going to talk about that in a few minutes. The part about partnering with industry partners is very important because we believe, and other experts in the field like Gartner agree, that building a unified approach to IT and OT security monitoring governance is important for several reasons. Number one, scarce resources, being able to use them across both IT and OT. And number two, most of the attacks we've seen cross from IT to OT and sometimes the other way around. So having a unified approach helps you more easily spot and investigate those attacks. And finally, the companies that are implementing this type of technology, the large manufacturing and companies in other industries like oil and gas, pharmaceuticals, energy, are looking for a single point of accountability for all of their digital risk. And that includes both IT and OT cyber risk. And here's some examples of the partners that we have been working with. We have the first and only native certified applications for Splunk, the first and only certified native applications for ServiceNow, for the Palo Alto Application Networks, Palo Alto Networks application framework, and we had the first certified native app for IBM QRadar. And so again, you can see that our commitment to helping you unify IT and OT security monitoring in the SOC has been going on for a while. We've been dedicating resources to it. It's not just a marketing campaign. In terms of the challenges we address, there are three core challenges combined with the unified monitoring that I was just talking about. Number one, what devices do I have? How are they connected? How are they communicating with each other? Most of you know that over the years, not all organizations have been doing a great job of tracking what devices they have, what manufacturers, what protocols they're using, what vulnerabilities they have. And so one of the first things that the Security Operations Center needs to know is, what devices are out there, how are they connected, so that we can do a better job of investigating when we get an alert. The risk and vulnerability management part is important because everyone knows there are vulnerabilities in these environments. Some of the devices are 20 years old. Some of them are difficult to patch. Many are still running Windows XP. So how do you prioritize the most important vulnerabilities to protect your crown jewel assets? Because you can't fix everything at the same time. And then the continuous monitoring part is the relevant to the behavioral anomaly detection covered in the NIST report. How do we continuously monitor all network activity so we can quickly identify a breach when it first occurs and quickly respond to it and mitigate its effect before it can get destructive or disruptive. In addition to providing our platform for asset management, risk management, and sorry about that. Okay, we seem to be having a problem here. We also were the first company to create an in-house ICS threat intelligence team. Okay, it seems to have a mind of its own. And we've reported nearly a dozen zero-day vulnerabilities across all of the industrial automation vendors you see there at the bottom. So our team is very familiar with these devices across multiple different vendors, across both process control and the discrete manufacturing, and across different geographies worldwide. And this intelligence is delivered to our platform through software updates, but also provides very deep information that we use to identify what might look like anomalous activity in our platform. So the threat intelligence enriches the built-in analytics that we were talking about a few minutes ago. In terms of deployment, the system is non-invasive and agentless, so very easy to deploy. It works by monitoring span port traffic, so it's passive monitoring. We use deep packet inspection and network traffic analysis to identify the assets and the threats. Once you plug it in, that's all you need to do. You don't need to sit down and write rules or download signatures. It's based on a behavioral analytics approach that does not require doing any of that. It's based on the embedded knowledge that's in the system. In terms of the platform architecture, we talked about the key use cases up at the top, and there's a REST API, and as I mentioned, a number of native apps for most commonly used tools you would have in your security stack. The key, though, is this middle section here where we have 5 distinct analytics engines to detect anomalies, not just simply relying on baseline deviations, although that's part of our patent, is the way we look for baseline deviations in a way that minimizes false positives and false negatives, but several other mechanisms that'll show up in the examples we're going to see in a few minutes, one of them being protocol violations. If an attacker is misusing a protocol in the way that it was not designed to be used by the designer of the protocol, the vendor that built the industrial protocol, that could indicate an attempt to compromise a device or the protocol itself using a vulnerability. There might be function codes or values that were left undefined that the attacker is now using, and we're going to see that in an example in a few minutes. So that would be an example of an analytics engine that detects anomalies without relying solely on deviations from the baseline. We also have an engine that looks for operational issues. This is more relevant to the folks in the plant than to the folks in the security operations center. This would be indications of unusual activity that could indicate malfunctioning equipment or misconfigured equipment. And we've found in our customer base that the data that we collect makes it very easy for the folks in the plant to troubleshoot those issues and identify the root cause. At the lowest level, of course, is a deep embedded knowledge of all the devices and protocols, our threat intelligence, which I mentioned before, and a unique in the industry capability called the Malware Analysis Sandbox, which allows you as a customer to upload suspicious files that you think might be ICS malware, have it analyzed in our ICS specific environment, and then the system returns with IOCs. So this is to address the fact that there are lots of sandboxes out there, but they were designed for IT, not OT. So if a piece of software is communicating on a given port that's unique to OT, or using a DLL that's unique to OT, most of the IT sandboxes won't really know what to do with that. So that's why we built our own malware analysis sandbox. And of course, central management console for getting a unified view of risk across all of your facilities worldwide and all of your business units with role-based access control to give different groups different access to different parts of the organization. And as I said before, the analytics engines are the key part that we're going to talk about here relative to the NIST study. So why is behavioral analytic and anomaly detection important nowadays? This is a report that came out recently from CrowdStrike, and what they're reporting is that the number of attacks that do not rely on malware is growing. It's up to 40%. And in fact, if you look at certain geographies like North America, almost 50% of the attacks do not rely on malware. And it's also a pretty high number for Europe and Indo-Pacific region. And so that means that attackers are getting smarter. They're not relying on signature, they don't need to worry about signature-based solutions in the environment because they're not using malware that can be identified through signatures or common IOCs. You can think of it as zero-day malware, but you can also think of it as people using stolen credentials, sort of diskless attacks, like using PowerShell, or even more recently, we've heard both from Cisco and then just recently in the last couple of days about compromises of routers that have, don't use malware that would easily be detected by signature-based solutions. So it's important to look at behavioral-based anomalies, because that's what you need to identify malware that's never been seen before or targeted attacks. And there was a great quote in this piece from CrowdStrike saying the important question isn't, how quickly can you prevent the initial compromise? It may be impossible to prevent a determined attacker from getting into your environment. What's really required is to be able to very quickly detect that an attacker is in your environment and then investigate and remediate or contain the threat. And that's how we help our customers in the ICS space specifically. The other reason that we need to look at behavioral anomaly detection is that these environments, as you probably know, are vulnerable, insecure by design. There are many vulnerabilities. This is a report you can download from the URL at the bottom left that looks at network traffic data that we collected from over 850 production ICS networks across all of the industrial sectors and across multiple continents worldwide. And you can see some of these things may not be surprising to you. The fact that nearly half of the sites we analyzed are still running unsupported versions of Windows like XP, making them very susceptible to attacks. Nearly 2/3 are still using plain text passwords on their network, which means if an attacker gets in, they can very quickly snip the traffic and monitor for plain text passwords that they can then use to get into other systems. And also this idea of the air gap that many, some less now than a few years ago, believe is the only protection they need. The air gap has long been believed to be mythical. What we found is that nearly half of the sites we analyzed had internet connections, either because they didn't know about them or because there were connections, multiple connections between IT and OT subnets that were not being monitored or segmented. Certainly very flat networks. We found a lot of those across both IT and OT. And then some cases just might be, a control engineer needs access to the internet when they're in the OT network to be able to look up a vendor, industrial automation vendor's documentation, and maybe they put in a dual-homed Ethernet card in their device, in their laptop to be able to do that. So these are other reasons why it's easier and easier for attackers to break into these environments. So I'm going to talk about TRITON. This is an attack that many folks have talked about, and you may be thinking, why are you talking about it again? I'm going to talk about it for two reasons. One, there was some new information released in January at the S4 conference that showed some interesting details about this attack that we didn't know about before. And number two, many of the tactics that the attackers used showed up in the list of anomaly scenarios that NIST put together. And NIST put this list together before we knew anything about TRITON, so it's kind of interesting. For those of you who are not familiar with TRITON, it was an attack launched on a petrochemical facility. And what was unusual about it is the attackers went after the safety controllers in the plant, and they compromised those safety controllers. And the idea was that they were going to disable the safety controllers, then cause something else to happen that would blow up the plant, cause loss of life, potentially environmental damage, because the safety controllers would no longer be able to shut down the plant, which is their job if the temperature, for example, or the pressure goes above certain thresholds. And that's what was unusual and caught the attention of many companies, not just in the petrochemical industry, but in all industries. So I'm just going to go through and show you kind of a quick description of the kill chain. We were guessing about some of the elements of this kill chain when we put it together shortly after the attack occurred, but turns out we were right about some of this. So one of the things we're not sure about exactly how they got into the network in the first place. We're going to guess that they stole OT credentials, since this is probably the most common approach. It was the one mentioned in the FBI DHS report last March about Russian threat actors being in our critical infrastructure. But by using those stolen credentials, they were able to go through the firewall between OT and IT and through the DMZ and install malware on one of the Windows-based devices in the OT environment. We don't know which one. We're going to guess it was the engineering workstation. Could have been the HMI. This was Python-based code that had been compiled to run on Windows. And here's where the interesting part comes. This code was purpose-built to communicate directly with the safety PLC using its native ICS protocol, which is the tri-station protocol. So these attackers knew enough about this environment that they knew those were the devices in the environment. They were Schneider Electric Triconic safety controllers, and they were probably doing reconnaissance in that environment for months before. The way we discovered that this attack was occurring was they made a mistake in the code, and the safety controllers shut down the plant for a week. And we're going to see some information about that in a second. So the idea was to take over these controllers. The attackers actually installed a remote access Trojan into the firmware memory region of the PLC, so they knew enough about the memory layout of that device to be able to insert their backdoor without disturbing its normal operation. Very sophisticated attack. And the idea was that they would then disable the safety controller and launch a second cyber attack, causing loss of life, certainly asset damage, and potentially environmental damage. So a behavioral anomaly detection system like ours would have detected strange things going on multiple times during the skill chain. Number one, the remote access connection from OT to IT to OT. Number two, during the reconnaissance phase, the attackers were likely doing address scans and port scans. Number three, they uploaded new ladder logic code into the PLC as a precursor to replacing the firmware or putting their backdoor into the firmware. So that would also be detected. And then finally, the fact that they were using the Triconics protocol in a way that it wasn't intended to be used would also have been flagged as a protocol violation. That's one of the analytics engines I mentioned before. And I'm going to show you exactly what they did. It was very sophisticated. We reverse engineered this malware early last year. You can see a full report on our blog at the URL below. We also posted some snort signatures for the attack, but of course, snort signatures, would only help you if the attackers use the exact same code. So I think a behavioral approach is much better. But if you look at what they did to get into the PLC, they used a standard command that's part of the Triconics protocol called get MP status. It's not used that often, but this command has a special identifier, and or they inserted a special identifier such that if there was no identifier, the command proceeded into the PLC as it normally would, and the original code that was intended to be executed in the PLC got executed. However, if that field in the command had an FF in it, the code that they put into the PLC would then check to see if it had an FF, and if it did, it was a way for them to communicate with their backdoor. So if the opcode associated with that special identifier was a 17, it meant we're reading the memory in our backdoor. And if it was a 41, it was a write memory, and if it was a F9, it was execute code. So you can see this is very sophisticated. They built their own modification of the native Triconics protocol so that they could communicate with their backdoor. And all of these things, as we're going to see shortly, would have triggered alerts from a behavioral anomaly detection system. So some new information came out in January at the S419 conference that was kind of interesting. Number one, there were actually two incidents, not one. There was another incident a couple of months before where the plant was shut down when the safety controller was tripped. The plant folks called in their automation vendor, which concluded that it was a mechanical failure. So they missed a really key opportunity here to identify a cyber attack. And this is another reason why security teams from the SOC need to have visibility into what's going on in the plant, because they can provide additional insights when these incidents occur. It may be a mechanical issue, but it may not. So you want to catch that early on. The other fact that came out of this presentation at S4 is that the second incident actually affected 6 safety controllers, not just 2. This is when they shut down the plant the second time. So you can think of hundreds of $millions of downtime and cleanup just from these accidental shutdown, not to mention the danger from some toxic gases. And then finally, in the incident response, there were multiple red flags that were ignored. The firewalls were misconfigured, so that allowed the attackers to very easily move from IT to the DMZ to the OT network. There were AV alerts on the workstations that were being ignored that would have told security teams that Mimikatz credential stealing malware was being used. There is something called the run program key on these safety controllers. You're supposed to leave it in the run key most of the time and put it in the program key only when you're updating ladder logic code, which is what the attackers did. They uploaded ladder logic code. Anecdotal evidence suggests that most organizations just leave it in the program key all the time because it's a pain and may actually be dangerous to go out onto the plant floor, or in this case, a petrochemical plant, to switch the position of the key. And then finally, suspicious RDP sessions from the IT network to the plant's engineering workstations. Again, an example of remote access from the IT network to the OT network that could indicate something suspicious and unauthorized going on. And I'll point you also to the 3 articles at the bottom there, Dark Reading, Cyberscoop, and EE News. Excellent articles reporting on this talk that was at S419 with more details. True lesson, though, was not so much technical as organizational, which was that there were clearly missing definitions about whose role it was to ensure that controls had been properly implemented and that were actually effective. Was it IT? Was it OT? Was it the integrator that built the plant? Was it the automation vendor that supplied the equipment? There was clearly a miss here from an organizational point of view that might have prevented this attack early on. So now let me move on to the anomaly scenarios in the NIST report. There's 15 of them. I'm not going to go through every single one of them. I just wanted to show you the full list, and I'm going to pick 5 or 6 to give you an example. Starting with really easy ones like unauthorized devices connecting to the network and the use of plain text credentials, going to the reconnaissance phase with the scan, remote access session, in this case through SSH, data exfiltration, logic download, and the protocol violation example I was talking about before. And then all the ones below there, we're going to leave you. You can go read them in the report. Denial of service attacks, brute force password attacks. These are also in the report. The way alerts show up in our system is in 2 ways. One is in this timeline, another is in an alert dashboard, and you can bounce back and forth between them. So the idea here with the event timeline is this gives you a good way to go back and investigate the incident and look at what else was going on at the time. And these aren't all alerts. Some of them might be a notice. A programming update to a PLC might be a legitimate update, but you want to know about it and you want to have a workflow for knowing who to call in the plant, which automation engineer to call to find out if this was legitimate or not, or if it happens on a regular basis at a certain time. But you can see the variety of alerts that you see that are identified by our system. It's really hundreds of different scenarios, behavioral scenarios that our system identifies, including some of the ones we've been talking about today, like remote access connections and things like that. So the first one was unauthorized devices connected to the network. This is a classic anomaly that all of our customers want to know about. Did a contractor plug their laptop into the network? Did an employee plug their laptop into the network? Did somebody at the plant level buy a new device and put it into the network without telling anybody? You want to know about that right away, and you want to have a workflow for executing it. And for all of these, at the bottom, I'll be showing some of the text that I pulled right out of the NIST report explaining either the severity or the importance of the anomaly or how it was simulated in the testbed environment. So that's what you see down there. Second one is the use of unencrypted credentials. In this case, it was using HTTP instead of HTTPS to get access, in this case, to a directory. And it was immediately identified as something that we should know about. Polaris in the test bed environment was the engineering workstation that was part of the standard simulated environment. The next one is an address scan. So both address scans and port scans are important. As NIST describes at the bottom, this is a way for attackers to locate vulnerable services, vulnerable devices in the reconnaissance phase. And the reconnaissance phase can last, for months. I mean, in the case of the Ukraine grid attacks, we know that guys were in there for a long time as well. And here you can see that the system immediately detected that address scan, and there'd be a similar alert for a port scan. Next one is a remote access section. In the TRITON case, they used RDP. In this case, it was SSH. In this case, actually, it was SSH going to the internet. So it was a, sorry, not going to the internet. That's the next example. So this was an example of someone using an SSH connection from the engineering workstation to a server. Oops. Next one is data exfiltration to the internet. I mean, the attackers need to have some way of communicating with their software that's installed in your environment. So they're going to find some way to do it. In the case of InDestroyer, which was the Ukrainian grid attack, they used Tor as a way to do it. This scenario was testing the ability to detect someone trying to exfiltrate data using the DNS protocol. It's a good way to do it using DNS because no one really monitors DNS for unusual activity. So this would be a way to exfiltrate data, for example, about what devices are in the environment, what firmware levels they have, and things like that. And then this one, again, if you think about our TRITON example, they downloaded or uploaded, however you want to say it, new ladder logic code into that safety controller. And then they used that code to insert their backdoor into the firmware memory region. So in this case, you can see it was, in this case, we were using the Ethernet IP protocol. And at the bottom there, it's explaining how it was simulated using the Allen Bradley software. There's a nice note there about physical access was required in order to change the operation mode from run to remote run. That's that key I was talking about before. And as I said before, often that key is just simply left in remote run. And then finally, the protocol violation, similar to what the TRITON attackers did in usurping the Triconix protocol. Here, we're using a simpler example with Modbus, where a function code called 49 was used with Modbus, which is not allowed. And you can see also at the bottom, there's a notification the PCAP file exists. So in many of these alerts, we'll capture the full PCAP file so that you can do a deeper dive if required. Just give you an idea of what the alert flow would be in a typical scenario. So you get some alerts. Again, they can come from the alert dashboard. I'm looking at them here on the timeline. In the case of a firmware update, you can click on that alert and get some more information about which devices were involved. You can then click on those devices and see where they are in the map. So this is a full map arranged by the Purdue model of your devices that we discovered, auto-discovered in your environment. So this is part of the asset discovery phase. But in terms of the incident response phase, once you click on that alert, it'll tell you, yeah, this was the device in question. So you can see how it's connected to the other devices. And then you click on that device and it actually says, and here are the devices that it regularly talks to, in this case, the engineering workstation and the HMI, which kind of makes sense. You can then click further and get details on each of these devices. Who makes the device, what operating system it's running in the case of a Windows device, what protocols is it using, what IP addresses. In this case, you can see there's 2 MAC addresses for this device. And then if you want to find out about the PLC itself, turns out it's an Emerson device, speaking Delta 5. And you can get even further information to find out about the serial number, the version that it's running. Is it an authorized device? In other words, is it a known device to the organization? Does it regularly scan, which in this case, the controller would not, but if it was a more SCADA type device, it might scan as a standard part of what it does. And then again, you can see down there some more information about IP address and MAC address. So very detailed information, again, to give visibility to the SOC team so they can better understand what's going on. It's another reason why IT security tools aren't really suited for this environment. They don't know what these protocols are. They can't do network traffic analysis on these protocols to understand their payloads. And they certainly don't know anything about these types of devices, especially the embedded devices. I'm going to wrap up with a description of part of the methodology that Idaho National Labs has defined. There's actually a full SANS webinar on this that you can go find on our website. All of the SANS webinars we've done are on our website with a transcript. So if you don't feel like watching the recording, you can just scan the transcript and look at the slides. And this was a webinar we did with Andy Bachman at INL a few months ago. Great quote: if you're in critical infrastructure, you should plan on you are going to be targeted. You know, you will be targeted basically. And if you're targeted, you will be compromised. It's that simple. So it's very similar to what we heard at the beginning of the presentation from the folks at Cylance, which is, it's not how do you avoid being compromised, how do you quickly identify if you have. I'm going to focus on one of the 4 steps here. The method here is identify your crown jewel processes. In other words, the one whose compromise would cause a major issue to your firm, either in major environmental issue, safety issue, revenue issue, a major production line goes down. Map the digital terrain, which is essentially build a topology map similar to what I was showing you before of all your devices and how they're connected. Illuminate the likely attack paths, that's the one I'm going to show you about, and then generate options for mitigation and protection. So in our system, when you go to the map, you can pick a device and you can say, you know what, this is my important device. You can either mark it as important or say simulate the attack vectors to this device, which is basically telling the system, knowing what you know about the topology of the network and the vulnerabilities of the network, can you tell me all the different ways ranked by risk that an attacker would use to compromise this PLC that I'm showing you here? The system then goes through and says, I found 3 different ways to get to your device, this PLC number 11. Here they are, ranked by risk, and then draws a picture of exactly what that attack vector or kill chain looks like. And this is also a very helpful way of explaining to your OT folks or to your business line of business folks who may not be so technical, to show them the risk to this PLC. In this case, there was a subnet exposed to the internet. There was no segmentation between that subnet and the other subnets. And then there were a bunch of vulnerabilities. You can then go through and you can simulate how you would mitigate this threat, either by patching those devices or by implementing better segmentation across those different levels. And we call this automated threat modeling, and it's unique in the industry. And again, it's a way to prioritize how you address the vulnerabilities in your OT environment. One of the ways to mitigate these types of threats is by integrating with the firewalls or NAC systems in your environment. In this case, we've done this with Palo Alto Networks, but are also doing it with other vendors such as Cisco and Checkpoint. The idea here is to pick a few key use cases shown in the middle there that when they are detected by our platform, you want to very quickly create firewall rules to block the source of the malicious traffic. So working with our customers, we picked 5 use cases, many of which we've talked about in this webinar, including PLC stop commands, which can break production, obviously. And what this allows you to do is very quickly, our platform will generate new firewall policies. An admin is still in the loop. Admin still needs to approve the policy and deploy it, deploy them to all the firewalls in the environment, the relevant firewalls. But it's a very quick way of streamlining that time between detecting a threat and preventing the threat. The other thing we've done in integrating with Palo Alto Networks is something we call granular network segmentation. The idea here is by monitoring the traffic, we can identify all the devices, what protocols they are using, which ones are authorized and unauthorized. And you can use this as a way to create segmentation policies in your Palo Alto network environment. So the idea is many organizations are now looking at how they can better segment their OT networks, but in order to segment them, you need to know which devices you have and how they communicate with each other, so you can make sure that the right devices are communicating with each other and the ones that shouldn't be communicating with each other aren't. And that's the second aspect of the integration we've done here, something that Palo Alto calls Dynamic Access Group, or DAGs, which is a way to create policies that are based on groups that can change dynamically. Like, example, all the Modbus devices should be able to talk to each other, but a Modbus device shouldn't be able to talk to a Emerson device, for example. The third level of integration is with something that Palo Alto has developed called their app framework, which was recently renamed to Cortex. This is a way of analyzing data that's already being collected by the Palo Alto appliances you already have. So if you already have Palo Alto appliances in the right spots in your network, what this allows us to do is to take the traffic from those devices and do much of the analysis I've talked about here today. And you can download this app from the Palo Alto Networks Marketplace. And again, we're the first and so far the only vendor to have done this with the app framework. Quick note on our customers, 2 of the top 5 US energy utilities in the US, names you would recognize, but also some of the largest companies in pharmaceuticals, chemicals, pipelines, gas distribution, and not just in the US, also across Europe and Asia Pacific region. And I'm going to give you an example of one of them. This is First Quality. They are a specialty paper manufacturer based in the US with plants across the US. And you can see here the benefit for them is the visibility that we give the SOC into their OT environment so they can apply unified security monitoring and governance. And specifically, they're now monitoring over 8,000 devices. They're using our centralized management system to give them global visibility at the SOC level. And they've integrated our platform with their existing SIM. In this case, it's QRadar, their orchestration system. In their case, it's Simplify, and their PAN Palo Alto Networks infrastructure. So in summary, what our clients tell us is we have the most mature and most interoperable solution, help you at multiple levels. At the strategic level, reduce risk. At the tactical level, gain visibility, allow you to prioritize your mitigations and to be able to detect and respond to threats quickly. And at an operational level, to very quickly integrate with your existing environments, both at the OT level in the plants and also in your SOC in a way that's non-intrusive and agentless. And we have some time remaining, so I'm going to look at the questions in a second, but for more information, I'll direct you to our resources page where you'll find a complete knowledge base consisting of our threat and vulnerability research presentations we've done at Black Hat, the global ICS and IoT risk report I referred to earlier, presentation on how to, an ebook on how to present OT risk to the board, and an executive guide to NISTIR, which is the first compliance directive directed towards critical infrastructure environments, came out of the EU. And then a bunch of events there where you can see us in the next few months. You can also download 2 chapters from Hacking ICS Exposed, which is the Bible in the industry for understanding the differences between IT and OT security, and a great way to get started if you're new to the field. And that's it for now. So let me take a quick look at the questions. We're doing great with time. Question, can CyberX behavioral anomaly detection be used to monitor and detect unusual activity in other aspects of this, not just in manufacturing plants, but also in building management systems? And the answer is yes. We are being used for that, and it is part of our capability. The protocols are a little different in those environments, but we've reverse engineered them as well. We understand those devices. And that's particularly relevant to, for example, data centers. If you're an organization that relies on your data center, like in financial services, or if you're a cloud provider, also if you're in the transportation industry, running airports, for example, they have building management systems, they have power management systems, and they have all the other control systems that we've talked about before for their automated baggage handling and various other things. So yes, definitely relevant to those other areas. And let's see. Yeah, question about NIST 800-53 controls. We do have some information about how our platform will help you address that. We also have some information about how we'll address how the various aspects of our platform address multiple dimensions of the NIST CSF. The slide that the folks from NIST presented only looked at the detect portion, but we will also handle the other portions as well, either directly or through integration with other products. So both the identify part, which would be relevant to asset discovery, the prevent part, which would be related to vulnerability management, threat modeling that I talked about, and integration with firewalls. The detect part we talked about, the respond part relative to incident response and forensics and integration with your SIM, and then the recovery part relevant to how you automate recovery activities and how you automate reporting to all of your stakeholders. Question about the pricing for these systems. That typically they're priced per site. So if you need, usually an appliance usually our customers are using one appliance per site, so it's priced per appliance. The appliances are standard Dell servers, so there's nothing special. We're not a hardware company, we're a software company, but it's a way to license the technology that I've been talking to you about on a per site basis, based on the number of devices you have at certain breakpoints. And obviously, if you're, as many of our customers are, if you've got tens or hundreds of facilities worldwide, there's a sliding scale of pricing based on that. And somebody asked, can you monitor multiple sites? The central manager that I talked about at the beginning is the way we do that. And again, there's role-based access control. Let me go to that slide so that you can get a unified view across all of your sites. One nice thing about our central management also is that you can set up logical zones to monitor. So you might have devices being monitored on one part of the plant by one appliance and another part of the plant by another appliance. But you want to think of them as a single logical zone. For example, a given production line system has the mechanism for defining logical zones.
Hey, Phil, it's Carol. I just want to let you know we aren't seeing your screen currently.
Oh, okay. Thank you for letting me know. How about now?
Yes. Thanks.
Okay, great. Yeah, so this was relevant to the question one of the gentlemen asked about, can you manage multiple sites from a single console? And that's what our central management system does. I think I'm going to wrap it up here, unless there are other questions or anything from the folks. Question, here's a question. Do you work with MSSPs? Absolutely. Many organizations don't have the manpower or resources to do this on their own. And we work with different MSSPs, IBM Security being one, DXC Technologies being another, Wipro being another. We'll really work with whoever you prefer as an MSSP, and we also offer our own expert ICS guys as a backup to your own team or to your MSSP team. So if sort of level 3 incident response is required, We have folks who handled incident response for their country, protecting their critical national infrastructure. These are guys who dealt with nation state threats day in and day out, who can then come on site and help with incident response, either for help your own team or to help the MSSPs. Okay, I think I'm going to wrap it up here. Thank you for your time today. Thank you, Mike and Jim and Tim from NIST NCCOE, A, for creating this project, and B, for helping us out with the webinar today. Encourage you to, if you have any other questions, send them to info@cyberxlabs.com. Down here, okay, I can't get to that so quickly. And Carol, thanks again for organizing a great event and all the logistics around it.
All right, sure thing. And thank you so much, Phil, Michael, Jim, and Zimmerman for Jim and Tim for your great presentation, and to CyberX for sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.